For quite some time now, we have been using the standard reduction potentials found in Appendix M in the back of your text to find the cell potential for the overall reaction, and then we use this value of the cell potential to see if the reaction is spontaneous or not. We've done this particular reaction lots of times. We know that this overall reaction of aqueous dissolved copper going to solid copper and metallic zinc going to dissolved zinc can be described by adding together these two half reactions, where this top one is the reduction and its associated reduction potential. The bottom one is an oxidation, and so this is the flipped reduction potential, because we have to do that for the, for the oxidation. We add these together and we get our cell potential. When we're doing this, you'll notice we write E0. What does that 0 mean? That 0 means that everything here is under what we call standard conditions. You've seen that symbolism before. Like when we draw a delta G with the 0 or delta H formation with the 0. This thing up here, that means standard conditions. And standard conditions means 1 molar concentration of all reactants and products. Or if it's a gas that we're dealing with, 1 bar pressure. And it also means a temperature of 298 Kelvin, 0.15, if you want to get, real specific. So this cell potential that we calculate only really counts if I've got 1 molar zinc ion, 1 molar copper 2 ion. These don't matter because they're solids, right? And if the reactions run at 298.15 Kelvin. Well, those are some pretty specific conditions. And obviously this reaction isn't always run under those conditions. So how do we calculate cell potentials for non-standard conditions? That's what we're going to cover today. What we do is we use something called the Nernst Equation. I'm going to write it here. The actual measured cell potential, notice there's no 0 here, so this is the cell potential that we're actually going to see on the readout, what it actually is. This is going to be the standard cell potential minus the gas constant times the Kelvin temperature divided by the number of moles of electrons transferred overall in the process, also divided by a constant called Faraday's constant. I'm going to tell you what that is in a second, times the natural log of the reaction quotient, Q. This takes on the form of the equilibrium constant. All right, so let's go over all these parts. F, that's going to be Faraday's constant. It's 96,485 coulombs of charge per mole of electron transferred. This is E cell. That's what we're usually going to be looking for. That's going to be the potential of the cell in question. So the cell potential. We know this. E0 cell, this is going to be the standard cell potential. R, we're going to use the physics gas constant, 8.314 joules per mole per Kelvin. T, therefore, had better be the Kelvin temperature. And Q is our reaction quotient. Oh, I didn't define N either. N is going to be the number of electrons transferred. All right, let's see this used in action. Let's say we have this equation. And we know we've already looked at the standard cell potential. We've calculated that for this. It's a positive 1.1 volts. Let's say that in our reaction, I only have, say, 1 times 10 to the negative 6th molar copper 2, and I have, we'll say, 2 molar zinc. Well, let's see. According to the principle of the Chatelier, we've got a huge concentration of this and a low concentration of this. This reaction is probably not going to be pushed as far as under standard conditions. So we'd expect our cell potential to be a little less positive. I don't know if it's going to go negative or not, but it certainly won't have a cell potential as high as 1.10 volts. Let's use our Nernst equation here and calculate what the cell potential will be. And we'll go ahead and assume we'll keep the temperature the same. We'll say it's the same as standard conditions, 298.15 Kelvin. So let's just see what's going on here. Now, fortunately, we have gone through the process of checking out the half reactions that are necessary to describe the overall reaction. You're always going to need to do that because you need to know how many moles of electrons are transferred. And it's going to be 2. So that's going to be important, right? That's one of the things that we have to know. I've got to know what N is. So let's see. I'm going to write down my equation. The cell potential, that's going to be the standard cell potential minus 8.314 joules per mole per Kelvin times 298.15 Kelvin. I'm going to divide that by 2 moles of electrons, right? Yep. And I'm also going to divide that by Faraday's constant, which is 96,485 coulombs per mole of electrons transferred. Of course, we're going to multiply this by the natural log of Q, and Q is going to be, if I write the reaction quotient for this, let's see, Q, that's going to be the concentration of zinc. Looks like I don't need to square because there's only one of them. And we're going to divide that by the concentration of copper. So let's just plug that in, right? Zinc, that's going to be 2 on the numerator. And it's going to be 1 times 10 to the negative 6 on the denominator. So I'm going to take the natural log of this. And I might as well go ahead and plug in the cell potential that I know what that is, positive 1.1 volts. Okay. So I'm going to take my negative 1.1 volts and I'm going to subtract whatever this whole thing is. I don't know what that is. I got to do the calculation. First thing I'm going to do is I'm going to check my units. Let's see. A coulomb, that looks like it survives. Here's a per mole and here's a per mole on numerator and denominator, so those cancel. And then on the numerator I have a per Kelvin and a Kelvin that cancel. And my unit that I'm left with, this is unitless over here. It's just going to be a number. My units are joules per coulomb. Hey, that's a volt. Well, that makes sense because I'm going to take this value in volts, and if I'm going to add something, I better be adding volts to it. So a joule per coulomb is a volt. Looks like I probably did things here correctly. Now all I got to do is make sure I do the arithmetic correctly with my calculator. All right, let's give it a shot here. There's quite a bit of calculation to do. I think I'm going to do this whole thing out here in front first. So I'm going to do 8.314 times 298.15. I'm going to divide that by 2. I'm going to divide that by 96,485. So all that stuff here, let's see, all that, not this, but this stuff here, that's going to be 0.0128. I'll go out 4 digits. So all this stuff here that I'm going to multiply by the natural log of this business is 0.01285. Okay. Now, let's do this part. 2 divided by 1 times 10 to the negative 6 is 2 million. I'm going to take the natural log of that, 14.5. So this here is 14.5, and I need to multiply that by 0.01285. 0.186 we'll go with. 0.186. That whole thing that I'm going to subtract is 0.186. So my cell potential under these conditions is going to be a positive 1.1 volts minus 0.186 volts. Let's see what that is. Make this positive, add it to 1.1, and it looks like our cell potential has dropped a little bit. It's dropped to positive 0.91 volts. It's still spontaneous. under these conditions, but it's not going to be pushed in this direction as hard as under standard conditions. You see here we have a potential that's about 0.2 volts lower than what it was when we started. I'm now going to take you through the problem on slide number 25 of the chapter 20 PowerPoint. It says a voltaic cell is set up at 25 degrees Celsius as follows. So this is the shorthand notation for a cell. And we're supposed to do three things. We need to write an equation for the reaction that occurs when the cell generates electric current. We need to determine the standard cell potential. And we need to determine the cell potential for the conditions listed. Okay, so the first thing we're going to do is we're going to write an equation for the reaction that occurs when the cell actually generates electric current. Well, let's look at this. If this here is our reduction potentials, we're going to want to flip this one if we want to generate positive current, correct? So I'll do that. I'll just write solid aluminum goes to aluminum 3 plus 3 electrons, and then of course I get to flip this because I made this an oxidation, and then the other one would just be nickel 2 plus 2 electrons goes to nickel solid, and because we didn't flip this, we leave this at a negative 0.25 volts. Well, notice here, I can't just add these together because these electrons don't balance, but they will balance if I multiply this top whole thing by 2 and this bottom whole thing by 3, right? So I have 2 aluminum solid, 2 aluminum ion, and 6 electrons, and then I'll need 3 nickels, 6 electrons, and 3 nickel solid. My electrons will cancel, and my overall reaction will be 2 aluminum solid plus 3 nickel 2 ions. Sorry, that should be, yeah, that's 3, that's correct. Yep, goes to 2 aluminum ions plus 3 nickel solid, and that's going to end up being if I add those together, that's going to be a standard cell potential of a positive 1.41 volts. So I've taken care of writing this reaction in a way in which it would generate electric current. And here's my standard cell potential. Now, fortunately, this also matches the way this cell has been written in shorthand notation, because remember, in a cell, we always put the oxidation on the left-hand side, and the reduction goes on the right. And if you notice, look, we've got solid aluminum and aluminum 3 plus being oxidized, right? There's the oxidation step. So that's awesome. And then over here we have nickel 2 plus and solid nickel and a reduction step. So this is great. What we've actually done, we've already done part B. We have determined the standard cell potential for this reaction, and that would be at 25 Celsius. And it would also be if this was 1 molar and if this was 1 molar, which is not the case. So now in this step, what we want to do is we want to determine the cell potential for the conditions listed. So let's see. I wanted the actual cell potential, which is going to be the standard cell potential, which fortunately we just calculated, minus RT over NF times the natural log of Q. Let's see if we can remind ourselves what all these things are. Well, this we calculated. This is what we want to know. R is the physics gas constant. T is our Kelvin temperature. N, do you remember what N is? Hey, that's going to be 6 electrons, isn't it? Remember we had to calculate this to be 6 to balance these electrons. And then F is going to be Faraday's constant. Now, what is the value of Q going to be? Well, that's our reaction quotient. So Q, we don't have to worry about solids for Q. But let's see, that's going to be the concentration of aluminum squared divided by the concentration of nickel cubed. So I think we have everything in place here. We can do some calculations. So let's see. I'll just write it here. E cell is E naught cell, the standard cell potential, minus NF RT over NF times the natural log of Q. Let's start filling things in. The cell potential, that's going to be our standard cell potential, which is a positive 1.41 volts, minus the gas constant, 8.314 joules per mole per Kelvin, times the temperature. We said that's 25 Celsius. Of course, I don't want to throw Celsius in there because that doesn't talk to the Kelvin unit. We have to convert that to 298 kelvins. We're going to divide that by N, which we remember is 6. You have to determine how many electrons are required to balance the redox reaction, or you can't use the Nernst equation. We're going to divide this also by Faraday's constant, which is 96,485 coulombs for every mole. And then I need to multiply that by the natural log of Q, which is the concentration of aluminum squared. So what's aluminum's concentration? 0.001 squared. And I'm going to divide that by the concentration of nickel cubed. What's that? 0.5 cubed. And I think everything is set. Let's do the math and find out. Well, let's do our units first. Just to remind you that these units should work. Per mole on the numerator cancels per mole on the denominator. Inverse Kelvin on the numerator cancels Kelvin on the numerator. And my unit is a joule per coulomb, which is the same thing as a volt. So these whole units, when I'm done, this is unitless, should end up as volts. That makes sense because I'm taking a unit in volts. And that means I need to be subtracting something that's in volts. Okay. I'm going to go ahead and calculate this part first, and then this part second. I'm going to call this A and this B just to keep track of it. And let's see. This part here should be 8.314 times 298. I need to divide that by 6, and then I need to divide that by 96,485. That's going to be 0.00428. I'll take it to 3 digits. And then part B, that needs to be the natural log of 0.001 squared. 0.001 squared. Oh, I'm not sure I did that right. 0.001, let's square it. And then I did divide that by 0.5 cubed. I'll just divide by 0.5 3 times. Okay, let's keep track here. Divided by 0.5, that's once. Divided by 0.5, that's twice. Divided by 0.5, that's 3 times. Now I need to take the natural log of that. So this part comes out to negative 11.74, we'll call it. Multiply that by, I got to multiply A and B, 0.00428. And it's going to be, all this together, it's going to be a negative 0.05 volts. Woo! Okay, so my cell potential is going to be positive 1.41 volts minus a negative 0.05 volts, so that means I'm going to end up adding it, which is going to be 1.46 volts. And it looks like our reaction got pushed in this direction just a little bit. It's a little bit more spontaneous than under standard conditions.